This video is going to be about the graphical interpretation of integration, calculating areas under a curve, specifically as relates to acceleration, velocity, and position. Previously, we saw that velocity is the slope of the position graph, and acceleration is the slope of the velocity graph. Let's look at the same scenario we studied previously in the context of slopes, but let's run the engine back the other way. Starting from acceleration, now let's go to velocity. And starting from velocity, let's go to position. The way that we do that is by the opposite mechanism of taking slopes. That turns to be calculating areas under the curve. Let's press play here, and let's watch the animation unfold. And then let's go back through and try to make sense sequentially of what's happening. Let's look first at the position diagram and remind ourselves of the motion there that's being represented. At time 0, we're at position 1. We're going to move forward in segment A at a steady speed. So we're going to move forward from position 1 to position 3 with a fixed slope. Then we're going to put the brakes on and go from 2 meters per second to a velocity of 0. Then we're going to start going backwards with our foot on the gas, speeding up, then still going backwards, but coasting into a slope of 0 on the position graph. So we're at rest at the end of segment D, and we stay at rest for all of segment E. What we really want to do, though, is to work in the other direction and see that the velocity plot can be thought of as a consequence of the acceleration plot, and correspondingly the position plot is a consequence of the velocity plot. So for our point of view now, let's imagine the acceleration plot is given to us. The acceleration plot, we know that accelerations times little steps in time are changes in velocity. So change in velocity is accumulated area under the acceleration versus time plot. Now, we're also going to have to throw in one bit of information as we go from acceleration to velocity, which is what velocity did we start off at? That's just got to be given to us. We have to stipulate it. It's not something that we can figure out based on the acceleration alone. So let's stipulate that the starting value of the velocity, in other words, the value of the velocity at time 0 was 2 meters per second. And likewise, let's stipulate, we just have to pick a number. Let's stipulate that the starting value of the position, the initial position, the position at time 0 was 1 meter. Now, relative to those starting positions, we can figure out changes in the velocity and also changes in position. Now, in this first interval here, what are we doing? As we go on the acceleration plot, interval A, from time 0 to time 1, the acceleration is 0. If the acceleration is 0, then there's no area accumulated between the function value and the 0 line. We're right on the 0 line. There's no area. There's no corresponding change in velocity. Another way to say that is if the acceleration is 0, we expect the velocity to just stay fixed. Now, on the other hand, something interesting was happening with the velocity relative to the position. Because we had a non-zero velocity, the position should be changing. Since the velocity was positive, the position should be going to more positive values. Let's look at that carefully. On that first time interval, we can see the area under the curve beginning to accumulate. As the area under the curve accumulates, the green area under the curve accumulates, the value of the position is increasing. The change in the position is equal to the area under the velocity versus time graph. At this moment right here, we're at half a second. What is the area that's in the green there? Well, it's got a height of 2 meters per second. It's got a width of a half a second. So 2 meters per second times 1/2 second, that's 1. In other words, each of these is half a block. Each block there has its height units in meters per second, its width units in seconds. So each block has an area of 1 meter. How many blocks are highlighted? 1 in total. How far have we moved forward? 1 meter forward. Let's keep playing the animation there. If I move to the end of segment A, I've got 2 blocks filled in now. How much has our position changed? It's gone from 1 to 3. There's been a positive change in position of 2 units. Let's stick with the velocity to position curve, but let's move now into segment B. Now we're slowing down. Oh, we're starting to see some area accumulated under this plot as well. Let's come back to that. We're slowing down. The velocity is dropping. So at the end of segment B, we had 1 second in time. How many blocks are filled in the green just in segment B? Well, that little triangle would fit neatly into that spot. It's equivalent to 1 total block. How much did our position change? It went from 3 to 4. 1 block filled in of the velocity curve, 1 meter positive change in velocity. What's the total change? The total number of blocks filled in are 1 block, 2 blocks, 3 blocks. What's the total change in position? From 1 to 4, 3 meters change in position. Now the velocity in segment C goes negative. So the area under the curve has flipped under the axis. We call that a negative area. At the end of segment C, let's see what's happened. That was plus 2 meters, plus 1 meter, minus 1 meter, plus 2, plus 1, minus 1. Altogether, that's plus 2. We went backwards 1 meter, sure enough, in segment C, and altogether our distance relative to where we started is still 2 meters forward. Now, let's go through segment D. Segment D, our velocity is still negative. The area under the curve in segment D was a total of -1 block. So we've got plus 2, plus 1, minus 1, minus 1. So plus 2, plus 1, that's 3, minus 1, minus 1, that gets us back to 1. Sure enough, all together, and it doesn't change in the last block because we're sitting still, all together, the total area under the curve was plus 1 meter. And what was our total distance traveled once everything had elapsed? Plus 1 meter. Let's see exactly the corresponding relationship now from the acceleration graph to the velocity graph. We know that little changes in velocity are accelerations times little steps in time. The height of the acceleration graph times little steps in width, steps in time, height times width, height in meters per second squared, width in second. So each block on the acceleration versus time graph corresponds to a velocity change of 1 meter per second. If the block is above the 0 line, it's a positive change in velocity. If the block is below the 0 line, it's a negative change in velocity. Let's go back to time 0 and let's watch the thing play forward again. In the first second, our acceleration stayed fixed at 0. Since our acceleration was 0, the velocity did not change. Now, in segment B, the acceleration drops to -2. We're starting to accumulate area under the curve, negative area in this case, because it's below the 0 line. So that's -2 blocks on the acceleration versus time graph. The accumulated area under the acceleration versus time graph is 2 meters per second, negative, because it's below the axis. How much has our velocity changed relative to where it started? 2 meters per second down. Let's continue in segment C. That looks like another -2. So we've got a total there of -4 blocks. How much has our velocity changed? It started at +2. It's now reached -2. So the total change in velocity was -4 blocks, or -4 meter per second units. Now, in segment D, the acceleration switches back positive again. The acceleration switches back positive. At the end of segment D, how many blocks have we got filled in? -2, -2, +2. So the velocity change in segment D alone from -2 to 0 was +2, but the total velocity change relative to where we started at time 0 is -2, -2, +2, -2, -2, +2, for a total change of -2. In the last interval, we're sitting still at a fixed position with a fixed velocity and a 0 acceleration. 0 velocity, 0 acceleration, fixed position. No further changes to the area under the acceleration graph. No further updates to the velocity. Once again, accumulated area under the acceleration versus time graph corresponds to changes in velocity. Accumulated area under the velocity versus time graph corresponds to accumulated changes in position. That's how we go from acceleration to velocity to position. Subsequently, we'll learn how to do that in equation form without necessarily having to have a graph in front of us, but that's always in principle and conceptually what we're accomplishing when we make this transition.